Hi class, today I'll be covering Lab 10, which is Beer's Law and Spectrophotometry. So let's get started. The easiest way to explain this slide is to look at the example first. So if you see there's a red solution, red colored solution. If a solution appears red, this means that the color that is being absorbed is green. So this is a color wheel. And they use the word complementary, which means opposite. So if you see a red solution, then green is being absorbed and anything across from this. So if you have a blue solution, orange is being absorbed, and you can pretty much see this here. Here's another example for me to explain it. This is taken from another instrument, not spectrophotometry that you will be using, but it kind of gives a better idea. A white light contains all colors in visible spectrum, and what will happen is that the green here, since this is red, the complementary or opposite color, will be absorbed. So you see this arrow has kind of disappeared, and your eye will only detect the red, while all the other colors will just pass through the solution. A spectrophotometer, sorry about that. It starts, I numbered these so you can look at the side. It has one, so you have a light source. It has a white light that contains all the colors. It will pass through a very narrow slit or of a beam onto a prism or grating. And it will then, as a prism, you'll see all the colors. And what will happen is that a specific color that coincides with a specific wavelength. So that means that wavelength, there's a numerical value that matches that color, will be absorbed through that sample. And what won't be absorbed, or it'll detect the difference. You see how this is a really bright beam and this is a very faint beam. There'll be a numerical value that will be given for this sample. And a spectrophotometer has two settings. It has absorbance and it has transmittance. Absorbance, A, has no units, usually does not have units. And here's an example. You see the arrow will go through and it'll detect how much of light will be absorbed in the solution. The less light that gets through, the greater the absorbance. Another measurement that is related to absorbance is percent transmittance. Percent transmittance is a measure of how much light passes through a sample. So absorbance is interested in how much is absorbed, and percent transmittance is how much is passed through the solution. An example is if light passes through water, what will be the percent transmittance? All light will pass through, so the transmittance is 100%. A colored solution is irradiated with white light that has all the colors. Some wavelengths will be selectively absorbed. A particular energy of light, which corresponds to a particular wavelength or color, is absorbed and disappears. So let's take a look at this color wheel. You see these numbers? This is all in units of nanometers. And a specific color has a specific numerical value that goes with it. You will never see something such as blue, which is 450 to 480 nanometers. You'll never see blue at 640 to 700 nanometers. Each color has a specific fingerprint or address, and that is always goes with that color. So that means energy. These are all energies. So a specific energy will either be absorbed or will pass through a solution. And if it's the correct energy, it'll get absorbed in that solution, and we can detect with the numerical value what that is. All the other wavelengths will simply pass through it. It will not do anything. When light is not absorbed, it is said that the light is transmitted through the solution. The more light a solution absorbs, the less light is transmitted through the solution. So for instance here, a solution will have its complementary color absorbed, which is orange. So complementary simply means opposite. And you have this color wheel you can always refer back to see what's being absorbed and what you're actually seeing. Absorbance spectrum. The absorbance spectrum is a graph of the absorbance of a solution at different wavelengths. So wavelengths, if you take a look here, you have absorbance on one side. This is the Y value. This is the X value. Wavelengths is in nanometers. And you have a blue solution. And the best wavelength is at 600 nanometers. So what happened here is the wavelengths were adjusted on a spectrophotometer and the absorbance values were collected, and then a graph was created with the values that were given. And you can see that the best value here was at 600 nanometers. What color would you expect the solution to be? Well, it's blue. Why would I know it's blue? Because 600 nanometers, if you go back, is orange. Since the solution is absorbing orange, it must appear blue, which is the complementary color to orange. Wavelength of maximum absorbance. So you always want to measure at the best wavelength. Why? Because you get the most accuracy. You are absorbing, you're getting the best values for absorbance, and you'll usually have several solutions. So you want to have the best starting out and not have faulty, because when you try to graph, that's when you'll see the problems occur. So again, this is called best wavelength, max wavelength. There's there's different ways to determine this. You can graph it. You can, usually visually the numbers will tell you itself when you write all these numbers down as you change the wavelength on a spectrophotometer. And then once you get the best wavelength, you will then test your solutions. Concentration and absorbance. Which of these two solutions contains a higher concentration of red dye? By just visually looking at it, you can see that the darkest is almost a brown. That is a higher concentration, which leads to a darker color. So that's very concentrated compared to the other side, which is a very pale pink color here. Which of these two solutions will have a higher absorbance at the best wavelength? A. The higher the concentration, the greater the absorbance. Now, keep in mind though that some concentrations can be too concentrated and you would actually have to dilute them. But in this case, we're just going to assume that doesn't happen for this lab and everything's fine. So A would be the answer. The more it's concentrated, you have a better chance of absorbance value, a higher absorbance value. What would happen if the wrong wavelength was selected? Nothing. You would get a 0 or a very small value. It would either absorb little or nothing at all. And these are numerical values that you would see on the spectrophotometer, so it would be very easy to tell that nothing is happening. Okay, so this takes us to Beer's law. So a spectrophotometer is used. You collect either percent transmittance or absorbance, and then you take that data and you usually graph it. You do not just use the instrument and walk away. This is usually information that needs to be graphed to show or indicate something with solutions. So Beer's law is a way to measure the concentration of solutions based on how they absorb light. The data is taken and graphed with a best fit line. Absorbance, no units, how much of a certain wavelength gets absorbed from the path through the cuvette. And this is the cuvette. It's what is the sample is stored in. It's usually quartz, and you have to be really careful not to touch anything because your fingerprints can ruin the lighting path, the light going through. It could refract it. It's just, you want to be very careful not to touch this as much. And there's usually these sides, you see it look frosted. Those are the sides you're allowed to touch, but never the clear sides. And when you place this in a spectrophotometer, you want to make sure that the clear sides face the beam. Molar absorptivity, it's dependent on the substance. A measure of how strongly a chemical species or substance absorbs light at a particular wavelength. A higher value means there's an increase in absorption of light. So if you have a very high value, that means that it's probably going to absorb a lot, and it's dependent on the substance. So you would need to, if you had a certain substance, you would need to look up the molar absorptivity. And here it does have units. It has molarity and centimeters, and they are on the bottom of an equation, if you had to look at it that way. So they are on the denominator side. I hope I'm making that clear. Path length is in centimeters, usually in centimeters. Width of the tube holding the solution, and it's usually 1 centimeter. If it's not, it should be specified. If it's not given, then it's always a default 1 centimeter, 1.00 centimeter. It affects how many of the chemical species the light will encounter on its journey. The higher value of B, the light will interact with more of that chemical species in the solution. So think of it as a path of trying to get to a door in a crowded room. The more crowded it is, the more you have to interact with people to get to the door on the other side of the room. The less crowded, the less interaction you'll have with people to get to that other side. And then C is molar concentration. It's molarity. The higher the concentration, the more moles you tend to have. There is an increase in interaction with the light. So think again of a crowded room. The more crowded the room is, the more the light will have to interact with more moles in that sample. Okay, so here's a Beer's law calculation. What is the absorbance of a 0.0054 millimolar red dye sample at 504 nanometers in a 1.0 centimeter cuvette? You would use Beer's law for this, and you don't need all the information that's given to you. You're not going to use the wavelengths here. It's given to you, but you don't need it. In some cases, if you had to look up the molar absorptivity, then some of this information would be given. Molar absorptivity is not here, but it was provided in this problem later. So I took this off lab flow, by the way. So you were given this. So you just plug in what you have and what you need. So you need absorbance, so A is what you're going to solve for. C is the concentration, and B is the path length. Now, this concentration needs to be changed to molarity. I did not do that here, but in the problem I did. So you can see that I changed it here. And then everything should cancel out. Why? Because absorbance has no units. So if you end up with a unit, you did something wrong. Okay, so this is blurry because I found it online and I wanted to use it. But unfortunately, I didn't know how to make it a little clearer, but I hope you can still see it. So let me explain what this is. Normally, you will find the best wavelength, and then you will collect absorbance readings for the solutions. You always have a blank, and then you have the rest. You can see 5 appears to be very concentrated, 2 is very faint, and 1 is should be DI water. 2, you have them numbered, and you have the C, which is the molarity. So as you can see, this molarity is going up with the more concentrated it is. Absorbance starts at 0, and you can see this is also going up. So the more concentration, the absorbance value is also going up. What trend do you predict for this relative absorbance readings at the best wavelength? The absorbance increases with increasing molarity, which is higher concentration. Okay, so I mentioned that you usually will not just collect absorbance values, you will be expected to graph it. In this lab, you will also have to do a graph. You need a graph with this data. So we want this best fit line. It's calibration curve, calibration graph. You are trying to, what you're going to do is graph your points and then put a best fit lab and some equations and R square on it. So I'm going to break all this down. All right, so first things, Beer's law. We've covered this as A, absorbance, molar absorptivity, B is path length, C is concentration. You will be expected to place an equation on your graph, which is y equals mx plus b. I'm going to break these down so you understand exactly what you're looking at. To graph this data, you can see A would be absorbance. Why would I tell you that? Because if we go back, this is the y value. This is your absorbance right here. That's just an example for that one. Y-axis, just in general, when you do graphs, just in general with this, y is usually the dependent variable. So in this case, it would be the absorbance, which is on the left side of the equal sign. The x-axis is the independent variable. This would be of the concentration. So this is on the right side. So x here is the concentration, A here is Y. So if you had to do a graph, X would have your concentration, Y would have your absorbance. I'm not really sure if I remember if this one, no, this one says wavelengths, but in this case it would be concentration, and this would be wavelengths. So this is your X value, this is your Y value. Okay. So here is, I found a graph that we can use here. If an unknown solution has an absorbance of 0.351, no units, what is its concentration? So this question is being asked to solve from the graph. So the information you've taken from a graph. This one has the y equals mx plus b equation. It doesn't look like that, but that's exactly what this is. And you're going to use this to solve this equation. So you have y equals 4.806x minus 0.0002. And you're going to plug in what you know. So you have the absorbance, you're going to plug in the absorbance. You're going to solve for x to determine what the concentration is at this absorbance. So that's what you're going to do here. You're going to plug it in, solve for it, and it's going to give you that concentration. Beer's law, molar absorptivity. So we're not done with this equation yet. We are being asked, and you may be asked in some parts of this, where is the molar absorptivity? So remember that B is 1.00 centimeters. Looking at the equation above, M is the slope. And how do you determine what the molar absorptivity is? You take the slope and you have it over B. If B is 1.00 centimeters, then the molar absorptivity is M. So in this case, that's going to cancel out, and it's going to give you, I think this one should have canceled out. I think sorry, I apologize. This unit should have canceled out here, if I did this right. Anyways, don't worry about the units right now. If I mess that up, I will give you credit for that. I'm already going to give credit for a couple questions on here. I'm just not going to tell you guys which one, because I want to make you guys actually do your best with this. Remember, M in the equation is the slope of the equation. So your slope is the molar absorptivity if your path is 1.00 centimeter. Okay? So you see there's the graph. You can take that number there, and that is actually going to be your number here. And here there's absorbance, and here's concentration. So this would be your X value. This is your Y value. Spectrophotometer. Now your video, there are videos, and some of the lab I think does explain some of this, but like I said, I'm not as happy at some of these labs because they don't really explain as well as they should. How to use the spectrophotometer. Turn on the instrument and the light source. So when you turn it on, you have two things you need to turn on. Turning on the instrument is just turning on the instrument. You actually have to turn on the light source, and it usually takes about 20 minutes to 30 minutes for that to fully warm up. While that's warming up, you prepare your samples and the blank. You select the correct wavelength and measure the blank after the light source has warmed up. How would you know what the correct wavelength is? You can turn the knob, and if you will take the value that's the highest. That would be your correct wavelength. So you would be able to visually see the numbers change when you do this. Most of the time you'll just get 0. And then eventually you'll start seeing the number go up, 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 and then you'll finally hit a peak, and then it'll go back down. Then you measure the samples. Once finished, remove the sample, turn off the light source and the instrument. So again, you're going to turn off two things this time instead of turning them on. These are very simplistic steps. You need to watch everything that's been given to you and read it, but this is an overview of a spectrophotometer. Okay, so you're asked to do 2 simulations. This one is concentration. It's not going to look as busy like this, but I'm explaining what's on here. So there's a blue knob here. This is going to put the water in the solution, and you can fill this up to 1 liter. Remember, if it's half, it says half here, but that's really 0.500 liter. You can evaporate the water here. This is a reset button. If you want to remove water, you pull the drain here. Here's your drink mix. Whatever you pull this arrow down, it's going to add here. And you can either shake this a lot and a lot of crystals will come out, or a very, very small amount and 1 or 2 crystals will come out. Now, nothing's going to happen unless you drag this magnifying, it looks like a magnifying glass, so I'm going to call it a magnifying glass. You're going to drag this, and you can leave it in here, and you will see the concentration change. So this is a quick overview of how to use this. There's instructions that you need to follow, but at least you understand now. This is you can see what's going on. Carefully pick your conditions and carefully pay attention to what is being asked. Then you have a second one with Beer's law. Okay, on this one you have your information here, your drink mix. This is your cuvette. This is the beam of light. And you have it preset, so when you do this, it'll stay on whatever it needs to, or you can make it variable and you can change it. And you have a reset. This one, do not move. Leave this in place because this beam of light has to come through the path of your sample and read here. But make sure you pick either transmittance or absorbance. Now, what can you do here? This arrow means that you can make this wider or smaller, and then you drag the ruler and you measure what it is that you have. Okay, so make sure to follow the instructions on this portion of the lab as well. So Basically, at the end of this, you're going to collect information and then you're going to graph. So this is a graph that I took. I don't know if this is off LabFlow. I don't remember now. It has concentration and it has absorbance. This person added the wavelength, so you know exactly what wavelength this is at. There's the best fit line. The best fit line here, you can see the data points on here. What is missing is the R-square. R-square is going to tell you how close these data plots are to fitting the line. So the highest number is 1, and anything below that is, so you usually will have like 0.999. That means it's really close, and the data points are almost exactly on the best fit line. And then you'll have your equation as well. Make sure you have units, make sure you have a title, and absorbance. There is no units, but you could put the wavelength if you remember to write that down. This is my sample. I graphed this. I told you I go through every lab myself several times on some of these. And of course, after I had already saved this, I realized that I didn't put the wavelength. I wish I had put the wavelength. Will it be counted wrong? Of course not. But you always want to give enough information to not have a bunch of questions directed at you. So you always want to be as thorough as possible. So here I have my concentration. It's molarity, so it's not just a title. You have to have your units. Absorbance, there is no units. I put standard curve for drink mix. I have my equation. I have my R-square. So this is telling me that my data points have fit into the best fit line very well because it's close to 1. So this is my information that I did based on I just randomly picked some numbers. I did the lab and I just randomly picked some numbers, and this is what I got. So here's some tips for you regarding this lab. This lab is kind of long. It's not a difficult lab at all, but it is kind of long. Pay close attention to the videos and take notes. Pay close attention to the worked out calculations. It's very easy to make mistakes or not read thoroughly what's being asked. Get comfortable with the simulations. Make sure you understand those before you even start doing the lab. And take data. Follow the instructions very carefully. I suggest you write everything down, everything. Because if you don't, you're going to have to go back and do the simulations again. If possible, print out this PDF lab so you can write all the information exactly where it needs to go on this lab. It'll really make things a lot easier for you. Give yourself enough time to complete. This is a little bit long, and you don't want to keep having to go back on things that you forgot or missed. There is a problem on this lab, the data report, I don't like. It's ask a question and then never covers it anywhere in the lab. And I don't agree with that. So it's on the data report side. It's the question is, what effect does the anion of an ionic compound have on the appearance of a solution? And I just caught that I wrote solution wrong, so I need to fix that. Answer should be B. It should be listed as B, but I don't know if LabFlow, moves the answers around. So don't just take it as B, look for the answer. The anion affects the color of the solution more than the intensity of the color. So when I do these labs, there's some problems that I really don't know where they got these from. They don't give any supporting information. So when I find that, I'll give you the question, or I might actually just give credit and not tell you guys on your side because I want you to do your best effort on it. Keep in mind, I do these labs, so I get frustrated with some of the stuff I see as well. And that's why I started to decide to do the videos to help you understand these. You shouldn't be struggling on, I'm disappointed. If these people are making labs, they should know what information they should be given. All right, so if you need help, please post under labs in the discussion. If nobody responds, let me know. I will send in an announcement and contact me, but give me enough time to respond. Okay, thank you.